Good morning. I'm Nick Gailer, doing Calorimeter for the measure of losses in electronic devices. This is an autumn session video for the presentation. So, my thesis is based around the fact that Australian power is at 230 volts, but is within a range of -6 to +10% of that. So that I'm giving you a working range of 216 to 253 volts, which is quite a large range, and many devices are not made for the extremities of this range, but they can still be powered by up to 250 volts completely legally, nothing wrong with that. So yeah, this chart shows that the preferred operating zone is 225 to 245, with the peak around 240 due to various reasons. Should I go through that? So those reasons, partially it used to be run at 240 volts, but it changed in the 20s to 230 volts as the standard, but due to supply, how it's done, it's still oversupplied. So 230 volts is the minimum that houses will get supplied at. And so the problems with measuring this is compact devices are extremely efficient with over 90% efficiency. This leaves a really small margin of error to measure the difference in losses. Traditional power loss measurement, so losses power in minus power out. Due to such a small issue, errors due to harmonics and phase errors can actually make up a very large percent of the error you find. So finding the error due to the supply voltage can be very difficult just due to the small losses that are found. A solution to this is to measure it directly, and in my case using calorimetric measurement to measure the heat that the device gives off. So all the losses that electronic devices produce comes as heat, light, sound, but almost all of this is heat in most cases. So what is a calorimeter? It is a device that isolates a test object in a controllable environment. So basically, it's a box that's sealed, so there's no heat transfer between the box and the ambient temperature, and you can control the environment to monitor or to see the effect of heat transfer. There's multiple different definitions. So there's passive or active. Passive calorimeters have no heating element in it, so the device or the test object produces all the heat that you want to observe. Active ones will have a heating element, and so they will heat an object until like a phase shift or something, and observe the effects. Full transfer, partial transfer, and no transfer is what I have labeled as how it does its heat transfer. So a no transfer calorimeter is just a completely sealed box that will heat up for a certain amount of time, and they'll just measure all the heat that's given off by the object without letting any heat escape. Partial transfer is one where heat will be allowed to leave the system, but it will be controlled in a manner. And full transfer is where the system has the same temperature as the outside system, and all heat is removed from the object. Open, single-jacketed, and double-jacketed types of passive calorimeters that are used with varying levels of isolation. Open calorimeters use air to transfer heat, and so they have two openings where air flows in and out. They're usually used for large applications because they're quite basic, and they have it's very difficult to find accurate losses with it. Single-jacketed is a sealed system with all the heat going through a single heat transfer device. And double-jacketed is the same, but has an air gap in between the inside chamber and the ambient temperature area. This air gap can be controlled to have almost zero heat leakage. Should I go through heat leakage? So heat leakage is, thermodynamics, the second law of thermodynamics states that heat will naturally flow from a hot source to a cold source. So by controlling the air gap, they can heat it to the exact same temperature as the inside, which means there'll be no flow because the heat is the same, so there's no flow in between them. And heat leakage is just heat flowing away that you don't capture. So a double-jacketed calorimeter is my intended design, or my design rather. Here you can see there's the ambient temperature surrounding it, the air gap, and then the enclosure with a device under test and a heat transfer unit. My design is a double-jacketed partial transfer passive calorimeter. The air gap is controlled, which will decrease heat leakage to almost zero, and because there's no heat leakage, all the heat transfer is controlled through the heat transfer device or system. So devices I'll be testing could be complex fluorescent LED, or lamps rather, which is the spiral lamp up the top, compact LED lighting, so downlights and stuff, similar to what's in this room, phone chargers as shown, and other small AC motors, roughly the same size as these things, just very small. My progress so far, I've done a lot of research, had a literature review and a large theoretical background. I analysed the feasibility of whether or not I could do this within the year and actually build it and test it. The basic design, so from the devices I'm intending to test, I've gauged my sizing from that and do some simulation and research, gaining some idea of materials. And so the simulation, I've done some basic simulations to test whether or not my assumptions about sizing materials and how the heat transfer will work are in fact correct. And so the simulation, I used a package in MATLAB called SimScape. They have a thermal modeling package in there. And so this is my designed simulation. It's all pretty confusing, so I'll break it down to the basic. So there's a device down here that heats a thermal mass, which is the air surrounding it, and the temperature is then sensed up top using like an accurate thermometer, but it's simulation. And then there's a heat transfer, has convective heat transfer. Yep. Through an aluminium plate to the ambient. So in this case, I have made this is a simulation of a single jacketed calorimeter because the air gap is unnecessary due to the idealness or the ideal nature of the simulation. This control block on the far right is how I've so far controlled the ambient side of the heat transfer plate. And so this is some results I've gained with it. So the axes, we have temperature on the y-axis, time on the x-axis, and the lines dictate the difference in temperature with the increase in losses of the device under testing. So it's clear to see the more losses in the device, the greater the temperature reaches for the system. So that was without any control of the ambient side, that was the ambient side to 20 degrees and the device just outputting whatever losses I had at. This is this is a simulation of controlling the ambient side to control the temperature inside of the enclosure. So the blue line at the top is what happens normally, and the red line is what happens when I control the temperature starting around 2 seconds. I decrease the temperature, which decreases the temperature inside it. Conclusions I've been able to gain from these simulations. Simulation acts as I wanted it to act, so my assumptions have been correct on how the heat transfer will occur. The ideal simulation has altered the performance, which is obvious. The settling time in research I've found has been, they've used over a few hours just to be sure, just to be sure the device has reached its final operating temperature or operating output. In the simulation, it was instant, so the settling time was very short. I'll need a feedback loop to properly dissipate the heat from the enclosure, and the simulation has made this apparent. Constant temperature measurements will be required, which adds another layer of complexity to my design. So for both inside, outside, and the heat gap, I'll need constant temperature to be able to accurately make an accurate device. Future of the project. In the spring session, I'll be refining the design, building it so it works, calibrating it using known devices, and then testing some devices with unknown properties against my original motivation, the Australian power system.